Hi class, good morning. So let us now come to the topic in refrigeration system. So by this time class, I will give you the effect of operating conditions. Okay. So there are several ways on how the performance of the refrigeration system was affected. Okay. So by this time class, so this is the effect of increasing the vaporizing temperature. So meaning we will increase from a lower temperature to a higher temperature one. Okay. So let us consider this problem class. A R12. Okay, so take note class, R12 is already phased out. Okay, so this is a refrigerant used by the refrigerator. Okay, so but anyway class, so in order to show, okay, uh, the principle used in refrigeration system, we can use any of the refrigerant. Okay, so AR12 simple saturated refrigerating cycle operates at an evaporating temperature of -10. Okay, and condensing temperature of 40 degrees. Okay, show the effects of increasing the vaporizing temperature to 5. Okay, so take note class from -10 vaporizing temperature to 5 degrees. Okay, so take note class at -10 the this is lower. So if water is under this temperature, so water is no longer liquid but it is solid. Okay, so because the freezing temperature of water is at 0. So take note, imagine this is at -10. So but here to 5 degrees, so water will not solidify at this temperature class. Okay, so considering now the uh, pressure enthalpy diagram class. So you will notice that this is numbered 1, 2, okay, 2, 3, and 4. So the original condition is 1, 2, 3, 4. So, but the other, in increasing the temperature of the, or the rising temperature, it is 5. So we numbered 5 degrees as 1 prime, and then 2 as, of course, 2 prime, and then 3 prime, and then 4 prime. Okay? So, but 3 prime class is the same as with 3. Okay? So, there is no change in location, of course, in the saturation curve. Okay? Okay. So, but the enthalpy, of course, at 3 and 3 prime are the same. Okay? So, let us now consider class the original condition. Okay? For the original condition, h sub 3 is equals to h sub 4. Since class, the condition here is isenthalpic. Okay? Constant enthalpy process. So, you can easily determine using the saturation table for R12. Okay? R12, look for the value of the enthalpy of liquid at 40 degrees. Take note class that 3 and 4 is, if you look at the pressure enthalpy diagram, the condition of the refrigerant here is in liquid state. Okay? So, but at 4, no longer liquid, but it is now in a gaseous form. Okay? But at 3, that is liquid. Okay? But the enthalpy, although there is a change in phase of the refrigerant, there is no change in the value of the enthalpy class. Okay? So, take note class. So, and then, for the -10 degrees evaporating cycle, so this is now the original uh, cycle class 1, 2, 3, 4 to 1 to complete the original cycle. Okay? So, getting now class the specific volume. So, since at 1, the condition of the refrigerant is in a gaseous form. So, we are going to look at the value of the specific volume of the refrigerant here. So, that is at negative 10. So, that is 0.07664. So, this is again class from the table. Okay? At negative 10. So, take note class that the process here is isentropic. The compression, of course, in the compressor is isentropic. Meaning from state point 1 to state point 2, the entropy are the same. Okay? So, for h of 2 now, that is equals to h of g at 960.65. So, or 961. Okay? So, take note class, this pressure here is obtained from 40. Okay? From 40 degrees. Okay? So, that is 960.65. If you look at the saturation temperature at 40 degrees, that is 900 or 960. Okay? 0.61. So, take note class that the entropy S2 is equals to S sub 1. Okay, so take note class here, 1 to 2. So, this superheated table for refrigerant class, so this curve from 1 to 2, that is isentropic. Okay? 1 to 2. Okay? So, and then, the value now of the enthalpy at 2, meaning at the end of compression, is 373 kilojoules per kilogram class. Okay? So, this is now the values. Okay? So, let us now consider if we increase the evaporating temperature to 5 degrees. Okay, so, the cycle now is 1 prime, 2 prime, 3, 4 to 1 prime. Okay? So, again, the condition, of course, at 1 is, or the condition is gas. Okay? So, looking at for the value of the specific volume of the gas at 5 degrees, so that is 0.047, 49 cubic meter per kilogram. Okay? So, getting H1 is equals to Hg at 5. So, 353.6 kilojoules. And at 2 prime, so that is again the pressure is the same as with the first condition. Okay, but take note class that the entropy here is no longer equal at negative 10. Okay, so this is different. The value is different. Okay, so the value now of the enthalpy at 2, of course, at the end of compression of the compressor is 371, which is lesser as compared to the previous value. Okay? So, you can easily identify class the value. Okay. H sub 2 is greater because the value here in this figure is all the vertical lines perpendicular to the abscissa is the enthalpy class. Okay? So, the horizontal line is the constant pressure line class. Okay? So, take note that the location of 2 and 2 prime is different. Okay? So, that's why the value of these two state points are also different. Okay? So, let us now proceed. So, here is now the effect, refrigerating effect. So, take note class that the refrigerating effect is the difference in enthalpy, of course, at the evaporator condition. Okay? At the evaporator. Okay, so, for the first condition, it is negative 10. Okay? Degrees Celsius. Okay. So, take note that the difference, H sub 1 minus H sub 4 is equals to 108.6 kilojoules per kilogram. And take note for 5 degrees, the difference, of course, of H1 prime and H4 prime is equals to 115.11. Take note, class, as what I have said, that H sub 4 is the same as with H sub 4 prime because the line, of course, perpendicular to the abscissa is, of course, the same, are the same rather. Okay? So, that is now the difference. Take note, class, that the refrigerating effect of the higher evaporating temperature is higher as compared to the previous condition. Okay, next. So, next is the effect on mass flow rate per ton. Take note, class, this is per ton. Okay? Per ton of refrigeration. This is not a weight or a mass. Okay? Ton. Okay? So, considering the negative 10 degrees Celsius evaporating cycle, the mass flow rate is equals to M is equals to 211 over H1 minus H sub 4. So, where does this 211 class came from? So, this value, take note that 1 ton of refrigeration is equals to 3.516 kilowatts. Okay? 3.516 kilowatts. So, changing this to kilojoules per minute, okay? Multiplying 3.516 multiplied by 60, that is equivalent to almost 210.6 something, okay? Or, we rounded up to 211 class, okay? So, getting now the mass, so that is 211 over the enthalpy at 1347.1 minus 238.5. So, the answer, class, is 1.943 kilogram per minute per ton. Okay? So, for the 5 degrees evaporating cycle, same formulas. Okay? So, substituting values, the answer now is 1.833 kilogram per minute per ton. Take note, class, that the effect on mass flow rate per ton will decrease. Okay? So, take note, the value for the original condition is 1.943 and for the increased evaporating temperature, 1.833 kilograms. Okay? So, next, class, is the effect on compressor volume capacity. So, for negative 10 evaporating cycle, the volume flow rate, of course, volume is equals to mass multiplied by the specific volume. So, take note, class, this formula is derived from the basic formula, density is equals to mass over the volume. Okay? But, specific volume is equals to the reciprocal of the density. Okay? So, that's why we get B1 equals to M multiplied by the specific volume. Okay? So, substituting values now, class. The value is 0.1489 cubic meter per minute per ton. Okay, for 5 degrees. Okay, so that is 0.833 multiplied by 0.04749. The value is 0.087 cubic meter per minute per ton. Okay? Next, effect on COP. So, take note, class, coefficient of performance. So, take note, class, that the performance of the refrigeration system is determined by just looking at the value of COP. Take note, class, that the higher the value of the coefficient of performance, the more efficient the refrigeration system. Okay? The more the refrigeration system performs. Okay? So, take note, class, that COP is also related to EER or the energy efficiency ratio. Take note, class, that COP, the unit used in COP are the same, both the numerator and the denominator. But for EER, the enthalpy at the or the change in or the refrigerating effect is defined in terms of BTU per pound. But the compressor work at the numerator is defined in terms of watts. So that is why EER is in BTU per watts. BTU per pound per watts. Okay, take note of that, class. So here is now the COP. So for the negative 10 condition, the value is 4.19, and for 5 degrees evaporating cycle, 661. Take note, class, that as what I have said, the more or the higher the value of the COP, of course, the more efficient is the refrigeration system. Okay? And next is the effect on work per ton of refrigeration. Okay? So, again, so work is equals to mass multiplied by H2 minus H1. So, take note that this is defined in terms or per ton. Okay? So, that is 1.943 multiplied by 373 minus 347.1. The value is 50.32 kilojoules per minute per ton. Okay? And that is also equals to 0.839 kilowatt per tons. And for 5 degrees, same process, the value is 31.89 kilojoules per minute per ton or 0.532 kilowatt per ton. Okay? So, another is the effect on condenser performance. Okay, so for negative 10 operating cycle, Q is equals to M multiplied by the change in enthalpy between the compressor and or at the end of compression and at the end of the evaporating or evaporator. Okay? So, the value now, class, is 261 kilojoules per minute per ton or 4.355 kilowatt per ton. And for 5 degrees, so Q equals to M, change in enthalpy, substituting values, the value is 242.9. So, and then, in kilowatt per ton, so that is 4.05 kilowatt per ton. Okay? So, take note, class, that the value of the higher evaporating temperature is lower. Okay? 4.05 only, but for negative 10, that is 4.355. Okay? So, here is now, class, the findings. Okay? So, effect of increasing the vaporizing temperature. 1. The refrigerating effect per unit mass increases. Take note, class. Once you increase the evaporating temperature, the refrigerating effect will increase. Okay? Another is the mass flow rate per ton decreases. The volume flow rate per ton decreases. COP increases. The work per ton decreases. The heat rejected at the condenser per ton decreases. Okay, class? So, I think it is now clear to everybody. Okay? Thank you very much, class. So, that's all about my presentation. Thank you very much.